We're going to talk about integration by substitution. If this video helps you, please like and subscribe for more math help, specifically, in this case, calculus. So, integration by substitution is used for integrating products or quotients. This is kind of your first check. And what we're trying to do is we're trying to isolate part of the function that we can assign to be a u, where if we found the derivative of u, that would appear in the problem, and then we could eliminate the fact that it was a substitution, or that it was a product or quotient. So let's do an example. I look at this and we have x squared multiplied by the cosine of x cubed. And I look at x cubed and I think, well, the derivative of that is 3x squared, which is really close to just the x squared. So I start by saying u is going to be x cubed. The derivative of that is 3x squared dx. By the way, I should just mention, oftentimes you'll see people write du dx equals 3x squared, and then they multiply the dx over. That is the reason the dx appears. Now, looking at this, we have a 3x squared dx. Here we have outside of our trig function, we've got an x squared dx. I would like it to be a perfect match. I would like it to be exactly 3x squared dx. So I'm going to put a 3 here, just like that. Now, obviously, you can't just take a function and multiply it by 3 unless you offset that with a 1/3 out front, because 1/3 times 3 is 1, and I haven't changed anything. So now, this part that I'm underlining, that is equal to du. So I can rewrite my integral. It's got a 1/3 out front. The cosine of u du. Again, just check that I made x cubed u, and all of the rest of this was du. Well, the antiderivative of cosine is sine plus c. And of course, we should end back with x's. So we resubstitute back in, and there's our final answer. Let's do another example. So this is integrating a quotient. So again, you start by saying, well, if I made u x squared plus 9, the derivative of that would be 2x, which is really close. And as you saw in the previous example, I can change that constant out front, that constant multiplier. And please be aware, that's all we can ever change. We can only ever change by a constant multiplier. We can't do anything else. If there was an x, for example, if this were x cubed and the derivative were 3x squared, we can't somehow add an x up here. If you encounter something like that, that means substitution isn't appropriate to use. So let's make u x squared plus 9. The derivative of that is 2x dx. Again, I'm so close in that numerator. I have a 3x dx. Now, if I could just make it a 2. So what I'm going to do is I'm going to multiply this by 2/3. So then the 3's will just divide out. Now, obviously, if I'm going to multiply inside by 2/3, I've got to undo that with a 3/2 out front. So my integral becomes 3/2 times the integral. The entire denominator was u. And because I now have a 2x dx, I can replace that numerator with just du. And I usually like to write it like this, 1 du. The antiderivative of 1 over u is natural log. I usually like to use a absolute value there because natural log has domain issues. I'm going to go back to x's. I should just mention we wouldn't have needed the absolute value because x squared plus 9 could never be negative. But here's our answer. Let's do one more. All right, let's do one that involves e. And again, usually with a situation like this, if substitution is going to work, it's going to have to be the exponent that is our u. So let's check that. If u were 4x cubed, the derivative of that is 12x squared. Again, you can't add x's. You can't put more x's in there, but we certainly can add or put a 12 multiplier in there to make it a perfect match, and offset that with a 1/12 out front. So we have our 1/12. in our rewritten integral. And it's going to be e to the u, because this was replaced with u, and then the 12x squared dx is all just going to be written as du. The antiderivative of e to the u is e to the u. Let's go back and finish up with x's. Like that. So again, we've got a multiplication here, 4x sine of x squared. So I look and I think, well, the x squared right here, if I found the derivative, that would be 2x, and I could manipulate this 4x to be that 2x. And again, that's all you can do is manipulate that multiplier. You can't add an x. All right? If this were x cubed, or if it were just x, let's say it were just x, well, derivative of x is 1. I can't add an x in here. So u is going to be x squared. The derivative of that is 2x dx. So I look and I think, how could I make that 4x into a 2? Well, I could multiply it by 1/2. That would make it 2. So I got to offset with a 2 out front. Always just the reciprocal. Okay. So we've got 2. The 2x dx is just going to be the du at the end. So this is just going to be sine of u du. The antiderivative is negative cosine. Negative 2 cosine of u. And we'll end up back with x's. So there's our answer. Again, substitution is for situations where you're trying to integrate products or quotients, and choosing one of those pieces, something in there to be u, can eliminate the fact that it was a product or quotient with du.